There are moments when you can feel that something is shifting. No loud bang, no big promise, just an inconspicuous detail that suddenly looks historic in the rearview mirror. Such a moment was when an NVIDIA H100 graphics processor left the Earth's surface. Not as an experiment in a lab, but as part of a functioning system in orbit. At first, that sounds like a curious footnote for tech nerds, but in reality, it could be the beginning of a completely new industry. Data centers in space. And before we dismiss this internally and put it in the science fiction drawer, it's worth pausing for a moment. Because 15 years ago, reusable rockets, global internet satellite constellations, or even private space travel as a serious economic factor sounded just as far-fetched. But even if we think further back to the Wright brothers who tried to build airplanes, back then they were also called eccentric crackpots and lunatics. Today, we are at a point where several developments are coming together. Artificial intelligence is exploding, the energy hunger of data centers is becoming a political problem, and water is becoming a scarce resource. And at the same time, rockets like Starship are lowering costs and multiplying the capacity to bring mass into orbit. This is no longer a thing of the future, it's an orchestra that's just starting to tune up. My name is Servan, and this is Mars. Chronicles, let's go. The infrastructure problem. Data centers have long been an invisible backbone of digitalization. Somewhere on the outskirts of the city, a few gray halls, lots of concrete, lots of electricity, that's it. But those days are over. Modern AI models have not increased the demand for computing power linearly, but exponentially. And we're only at the beginning of this development, which some might call a bubble. A single large AI training cluster today consumes power in the range of hundreds of megawatts, which is about the size of a medium-sized power plant. That's not an isolated case anymore, it's the new norm. As I said, this is just the beginning because these data centers are getting bigger and more energy hungry, and they're springing up like weeds. But the real problem isn't just the electricity, it's the waste heat. On Earth, this heat is dissipated with air or water, a lot of water. Hyperscale data centers consume millions of liters of fresh water per day, sometimes in regions that are already suffering from drought. In the United States, there are already several communities actively fighting new data centers because rivers and groundwater are measurably affected. In short, data centers are now directly competing with cities, agriculture, and industry for energy and water. And that's happening in a world that actually wants to electrify and decarbonize. You can optimize that for a few more years, more efficient chips, better cooling, new locations. But the fundamental problem remains. We're trying to scale an industry that physically is extremely reluctant to scale. And this is exactly where looking up suddenly starts to make sense, because now you can put a stop to the whole thing and hinder progress. Or you can ask yourself how to solve this sustainably, and that's exactly what some companies did last year, which behaves fundamentally differently in orbit. Different rules apply in space. Energy there doesn't come from the grid, but directly from the sun. In a sun-synchronous orbit, it shines practically around the clock. No night, no clouds, no seasons, but also no overloaded grids. And thanks to the guaranteed continuous sunlight, the need for batteries and accumulators drops significantly. But something else is even more important: cooling. In space, there's no air, no water, and nothing you could evaporate or use to dissipate the heat. Heat is only released through infrared radiation. That might sound like a disadvantage at first, but in reality, it's something you can plan for. With sufficiently large radiator surfaces, heat can be dissipated very precisely and continuously, without using water, without noise, and without moving parts. StarCloud addresses this point directly. At their core, their satellites are essentially flying GPU clusters with gigantic fold-out radiators that dissipate thermal energy in the form of infrared radiation. The first demonstrator already carries an NVIDIA H100, which is about 100 times more powerful than anything that has ever computed in orbit before. The crucial thing isn't this single GPU. What's important is that it runs stably up there, can be cooled, and that radiation can be controlled. That modern data center hardware isn't necessarily bound to the Earth's surface. And once that's been proven, doors will open that simply didn't exist before. Starship as the missing piece of the puzzle. All of this would be purely academic if transport into space remained astronomically expensive, but this is exactly where Starship comes into play. Fully reusable, payloads of over 100 and possibly even 200 tons later on. And above all, a production philosophy that focuses not on one-offs, but on mass production. Up until now, there was talk of 1,000 Starships per year, but recently Elon Musk posted that production could even reach 10,000 units per year, so about 27 units per day. For the Mars ambitions, the 1,000 would have been sufficient, but the new business sector requires a much larger infrastructure. Because in the future, only the chips are supposed to come from Earth. Everything else is supposed to be built on the moon and shot into space with electromagnetic railguns. A complete orbital data center module with about 40 megawatts of power and around 100 tons of mass could theoretically fit into a single Starship. This isn't a vision for the year 2100, but a realistic assumption for the early 2030s, when Starship is flying regularly. This dramatically shifts the economic equation. The central question is no longer whether you can bring data centers into space, but at what launch price per kilogram it becomes worthwhile. StarCloud arrives at a critical threshold of about $500 per kilogram, which is about a tenth of what is currently common. That's still ambitious, but it's a magnitude that, with fully reusable heavy lift rockets, at least no longer seems absurd. The elephant in the room. Cooling in a vacuum, as elegant as it all sounds, this is also where the greatest technical challenge lies. Cooling in space isn't a gift, it's a necessity for surface area. Radiators have to be huge. The more computing power, the larger the radiating surface. That means large, fragile structures, potentially vulnerable to micrometeoroids, complex to deploy, and difficult to scale. The engineers at StarCloud know this. Most of their team is working exactly on this issue. Building lightweight, inexpensive, foldable radiators with extremely high reliability is not a trivial problem, but it's one that at least fits neatly within the laws of physics. You can calculate it, you can test it, you can scale it up step by step. And that's exactly what sets this idea apart from many earlier space utopias. Up to this point, it all sounds like a fascinating technical vision, but technology alone doesn't build an industry. The crucial questions are only coming up now. Is this really cheaper than data centers on Earth? How quickly could such an orbital data center be built? Does a single large center make sense, or many distributed swarms? And what does that mean for Google, Amazon, NVIDIA, and energy policy on Earth? That's exactly what we're going to clarify now, why all of this makes sense both physically and economically. When talking about data centers in space, almost the same objection always comes up. Sounds nice, but you can't actually cool things in space. And this is exactly where the real misunderstanding begins, because cooling doesn't mean that air is blowing somewhere. Cooling means that heat is leaving a place. It has exactly one escape route: radiation, not convection, not evaporation, but electromagnetic radiation in the infrared range. According to the Stefan Boltzmann law, on Earth we make cooling complicated because we have to. Data centers consume gigantic amounts of electricity, and almost all of that electrical power eventually turns into waste heat. This heat is moved with air, carried away with water, or simply evaporated. That's why modern data centers are often located next to rivers or lakes, and that's exactly why they are increasingly coming into conflict with communities, agriculture, and environmental authorities. A large AI data center today can use several million liters of fresh water per day, not per year, per day. This is not a theoretical problem. It's already a reality in the United States and increasingly in Europe as well. The waste heat doesn't disappear, it's just relocated locally with all the political and ecological consequences. In orbit, it's fundamentally different. There's no air, no water, and no evaporation. But there's something much more valuable: the perfect heat sink. Deep space effectively has a temperature close to absolute zero. That means any surface that's warm enough can radiate heat extremely efficiently. Not fast in terms of speed, but relentless in terms of physics. The heat is taken directly from the chips, carried through liquid circuits to the large radiators, and then radiated into space as infrared radiation. Nothing is consumed, nothing is lost, not a drop of water, no cooling circuit that needs replenishment. The cooling is not limited by infrastructure, but by surface area. And this is exactly where the real bottleneck lies. Not the GPU, not the software, but the radiator. The more computing power you use, the larger the radiating surface needs to be. That's not a design decision, that's thermodynamics. Anyone doing calculations in space ultimately builds huge, extremely lightweight, rollable structures that resemble solar sails more than classic satellites. That's why the people at StarCloud openly say our most important product isn't the chip, it's the radiator. Although they don't build chips, they buy them. That sounds unspectacular, but it's the core of the business model. Because radiators scale, they need space. And space isn't scarce in orbit, but mass is. And that's exactly why everything is designed for minimal material density, maximum surface area, and reliable deployment. That's difficult, but solvable, and above all, it scales better than any cooling system on Earth. But even perfect cooling wouldn't help if a second factor hadn't changed everything. Energy. Data centers are no longer just information technology infrastructure. They are major energy consumers. The bottleneck is no longer the chip, but the power supply. Electricity prices are rising, grids are overloaded, and new power lines take years or even decades. Every new data center location is a political project, and every gigawatt of computing power competes directly with households, industry, electric mobility, and heat pumps. This problem doesn't exist in orbit. There's no power generation and no grid there. There's only energy-rich sunlight, constantly available and predictable, with no night if you choose the right orbit. The energy comes straight from the source and doesn't need to be transported, approved, or subsidized. The only cost that needs to be paid is transporting the hardware up there. The same goes for expansion. If you need another million GPUs, just launch them up. No need for complex environmental assessments, acquiring land, connecting to the grid, and so on. And that's exactly why one name keeps coming up here: Starship. Without Starship, this discussion wouldn't even exist. Point: the entire idea of orbital data centers depends on a single variable: the cost per kilogram to orbit. StarCloud says their business model is economically viable at about $500 per kilogram. That's not a science fiction number. That's a concrete target, and it's orders of magnitude closer than anything space-based solar ever would have needed. But the crucial point is not just the price, but the capacity. SpaceX is currently building a system that's not designed for today's demand, but for a future where millions of tons are supposed to fly to Mars. This capacity won't be fully utilized for years, and unused launch capacity is dead capital. What do you do with rockets that aren't currently flying to Mars? Exactly. You sell them at marginal cost, and that's exactly where space for completely new industries emerges. Another point that is often overlooked is the architecture of such data centers. No one forces them to be monolithic giants. On the contrary, there are many reasons to think of them as networks, either as large clusters working together or as swarms of many individual nodes orbiting around the Earth. Redundancy through quantity instead of perfection through size. The internet didn't become successful because of a supercomputer, but because of many small computers working together. It would be surprising if this principle was suddenly reversed in space. Here on Earth, computers communicate with each other through fiber optic cables, which basically means that laser signals are sent and received. The only way to transmit laser signals more efficiently than through fiber optics is through a vacuum, like in space. There, the swarms are supposed to be connected to each other via laser link, just like Starlink does. The timeline is still in question, and honesty, not exaggeration, is what's needed. Today we see prototypes, individual GPUs in orbit, demonstrations, and proofs of concept. In the early 2030s, we'll see megawatt-class systems, data centers that have to be taken seriously. From the mid-2030s onward, we'll reach the point where orbital computing becomes cheaper than new facilities on Earth in certain areas. From then on, the curve stops progressing linearly and becomes exponential. Because as soon as most new computing power is created in orbit, it becomes irrational to build it on Earth. And that leads to a question that goes far beyond technology. Who owns these data centers, and which laws apply in orbit? What happens when countries start operating strategic computing power outside their own territory? And how do you protect huge, fragile structures in an increasingly militarized environment? These are not marginal questions. These are the questions that determine whether we are talking about a technological curiosity here or about the beginning of the greatest infrastructural shift since industrialization. Money, power, and the point of no return. Up to this point, you could still dismiss all of this as an ambitious engineering project. Bold startups, visionary founders, a lot of risk, maybe a few spectacular failures. But this is exactly where the story takes a turn. Because data centers are not a niche topic. They are already critical infrastructure today, and whoever controls the infrastructure ultimately controls more than just servers. So let's take a look at profitability, not in marketing slides, but in reality. A modern hyperscale data center on Earth costs several $billions. It's not just about the hardware, but also the land, power, network expansion, cooling, water rights, permits, political deals, and more. And then it stands there, firmly anchored, dependent on local energy prices, local laws, and conflicts. In orbit, the cost structure looks completely different. The initial investment is brutal, transportation is expensive, the technology is risky, but once the hardware is up there, entire blocks of costs disappear completely. No electricity bill, no water, no grid expansion, no new permits for every additional megawatt. The ongoing costs drop drastically while scaling becomes easier. That means orbital compute isn't a short-term savings model, it's a long-term lever. Those who invest early pay more at the beginning, but start to benefit after a certain point. A structural advantage that traditional locations can no longer catch up with. And this point doesn't come gradually, it comes abruptly. As soon as new computing power can be provided in orbit more cheaply than new computing power on Earth, the market shifts. From then on, existing facilities will continue to operate, but new constructions will lose their economic justification. That is the moment when investments shift, not out of ideology, but out of necessity. And this is exactly where the winners emerge. Those who control three things at the same time will be the winners: initial capacity, access to energy, and chip supply chains. NVIDIA, Amazon, Google, SpaceX, these names don't keep coming up by chance. They are exactly at the key points that are crucial for this model. The losers are just as easy to identify. Regions that are heavily investing in data centers today will lose investments in the long run. Energy providers will lose major customers. Municipalities will lose revenue. And states will lose part of their control over critical infrastructure that suddenly lies outside their territory. And that turns a technology project into a geopolitical problem. Because what does it mean when a significant portion of global AI computing power is no longer located on national soil, but instead in international orbits? Which law applies there? Who intervenes if sabotage occurs? And how does a country respond when its economic or military capabilities depend on orbital infrastructure that it doesn't fully control? These questions are not hypothetical, and they're certainly not resolved. They're already being asked, just not in public. Another point that is rarely mentioned is the military dimension. Computing power today is just as strategic as oil was in the 20th century. Whoever controls training capacities controls the development speed of AI systems. Orbital compute is beyond the reach of traditional access methods. It is hard to sanction, hard to block, and even harder to destroy without risking massive escalation. At the same time, new vulnerabilities are emerging. Large radiators are sensitive. Orbital debris is becoming a real threat, a cascade effect. A Kessler scenario could render large clusters and even entire orbits unusable. That means traffic management in orbit will become a prerequisite for economic stability. Whoever controls that wields power. And then there's another point that hardly anyone talks about because it sounds almost absurd, but it's logically inevitable. If you consistently move computing into space, you inevitably end up with a simple question. Why just a few megawatts? Why not gigawatts? Why not terawatts? Why not systematically collect as much energy as is physically possible? From this point on, we're not entering science fiction territory, but rather extrapolated industrial development, Dyson swarms, Matryoshka structures, stellar computing. That sounds absurd today, just like global cloud infrastructure would have sounded absurd 50 years ago. But the direction is clear. Collect energy directly at the source and convert it into computing power. I've already made a video on the topic of Dyson spheres and Matryoshka structures, which I'll link below. Highly recommended. And that's exactly why this boom is so fundamental. It's not just a single market that's growing, it's a new endpoint for industry, energy, and information. And this brings us back to Starship, because in this context, Starship isn't the vehicle to bring people to Mars. It's the first industrial transport machine that makes this vision possible in the first place, similar to the transcontinental railroad. Mars is the narrative, compute is the business model, and energy is the real driving force. Maybe one day Starship will take millions of people to another planet, but before that, it will do something much more mundane. Start servers, deploy radiators, expand infrastructure, not for explorers, but for computing power. And when that point is reached, no one will ask anymore whether data centers in space make sense. Then people will only wonder why it took us so long to get started. Conclusion, not if, but when. When you add all that up, in the end, you're left with an uncomfortable realization. Data centers in space aren't some crazy idea from the Silicon Valley bubble, nor are they a marketing stunt for rocket fans or science fiction writers. They are a logical consequence of three trends that reinforce each other: exploding energy demand, increasingly dense computing power, and a planet that is becoming more and more unsuitable for this combination. Earth is excellent for inventing computers, but it's not an optimal place to run them indefinitely. Electricity here is expensive, politically contested, and ecologically limited. Cooling becomes a bottleneck, space becomes a conflict, and every additional expansion stage brings new permits, new dependencies, and new resistance. In orbit, many of these problems don't magically disappear, but they shift. Energy is not scarce there, but abundant. Cooling is not a cost factor, but a design question. Scaling no longer means negotiating with communities, but rather more launch capacity. And this is exactly the crucial point. The question is not whether data centers in space can become cheaper, more efficient, or cleaner, but at what point they become indispensable. Because as soon as the first player can show that orbital computing works economically, no one will stay on Earth out of idealism anymore. Then it's not vision versus skepticism that decides, but profit versus stagnation. Starship is not a savior in this regard. It is a tool, a very rough, very powerful tool that lowers a threshold that previously seemed insurmountable. That may be the most important point of this topic. Major technological upheavals always seem like an oversized detour at first, too expensive, too risky, too early, until suddenly they become the direct path. It was the same with container ships, airplanes, fiber optic cables, globalization, cloud computing, and many other fields. And it will probably be the same here. Maybe there will be setbacks, maybe the first system will fail, maybe it will take longer than the most optimistic forecasts promise. But if energy is abundant, if transportation costs drop massively, and if computing power remains the limiting factor for economic and political power, then the path inevitably leads upward. Not out of romance, not out of curiosity, but out of efficiency. And that's exactly why we're not talking about a distant future here. We're talking about the next logical step for an industry that has already begun to overcome Earth's gravity. If you like this kind of analysis, you'll find more of it in the Mars Chronicle newsletter. I'll put the link for you down below in the description. Take two.